0.4826 times 10 to the power 6 minus by 7.7409 times 10 to the power 9 y squared. Okay, so this is your first answer on the shear stress distribution. Now question, how do you know it's right or wrong? Anyone? How do you know if this distribution, this equation is correct?
Eugene,
Yeah.
if you put y as 0.035, you should get the maximum shear.
If you put y is equal to 0.035, you should get maximum shear. It's the opposite.
Oh,
If I put y is equal to 0.035, the whole equation is equal to what?
0.
There you go.
Mm.
Right? Right.
Mm.
So when you substitute y is equal to 0.035, okay, the shear will be equal. So I'm going to substitute that. Okay, so it's equal to 9.4826 power 6 minus 7.7409 power 9 times by 0.035 squared. I get minus 2.5. Which is approximately equal to what? 0. Okay, why? Because the maximum of the shear is the maximum you can achieve is what? 9.4826 times 10 power 6 based on this equation, yes or no? Okay, right? So based on why we say y is equal to 0.035, the whole thing will be equal to 0, because everything we apply rule number what? Rule number 1, right? We apply rule number 1 or rule number 2 that the datum of analysis is at the what? Centroid. So y is equal to 0.035. If you look at how we sketch our distribution, what do you see? When y is at its what? The shear stress is equal to what? 0. Okay, the shear stress is equal. That's why deriving this formula, okay, deriving this expression is so critical. Once you derive it, then you understand the limits of, or then you know how to apply that the shear stress is equal to what? VQ over what? IT. For that reason, okay? Right. So the next one, that we're going to do, okay, we are going to look at, we're going to form another limits. Okay, I need this diagram again. Right. So now, so we finished the flange section already. Now we're going to look at the web section. Okay, we're going to look at the web section. So the web section is from 0, or the web, the sorry, not just web, the top web section. Okay, the top web section. So the top web section, the limits will be 0, y, and you'll stop at 0.015 meters. Okay, so I'm going to draw it over here. So we know where our y bar is now. Sorry, our z. Right, so this is our zz. So we know the limits up to here. This is 0.015. Right, and this section over here is known as the web section. Right, and then the other one, this is our flange section. Okay, so one is our web and the other one is our flange. Okay, so that's why the limits is 0.015. Okay, now we have to be really careful about our first moment of area. Okay, so I'm going to draw again. I'm going to sketch. Okay, so we have this part. And then we have the other two parts. Again, this is just a sketch, okay? So this is one part. This is the other part. This is the other web. Right. So you can see this now. And then this is our ZZ axis. Okay. So now our slider now, right? Our slider is over here now. So now our slider, okay, good choice. Our slider is over here now. Okay, our slider is over here now. So this is our Y, right? And then we have our Y bar somewhere around here, directly at the center. So this is the area the equation will be formed for, right? But, so we know that this is our web, right? But however, we have to also include our what? Our flange. So we have to include this entire area now. We have to include this entire area. Now this entire area, regardless, the flange area, regardless of your Y, the flange will always be a what? Constant. I repeat again, right? Regardless of where your Y move, right? Your flange is always a what? A constant. Your first moment of area for your flange will always be a constant. Am I right? Okay.
Eugene,
Yes. Yes.
have a question. The Y bar, I thought that would be until the bottom of the flange. No? I'm
No.
confused at that part.
No. So you know why you're confused? There's another rule. The analysis starts from where? Y
From
max.
mm-hmm,
From the datum, but the analysis go from the Y. So the analysis direction is this way, yes or no?
mm-hmm, yes.
Yeah, there's Y. So it's not at the bottom, is it?
Oh, okay.
Right? So we apply the rules again, right?
Mm-hmm.
Right? We apply the rules again that states that what? That the analysis, where is it? That the analysis will be carried out when Y variable is as is what?
A maximum.
There you go. Okay, that's why you only know these rules when you derive the equation. What we've done in the first what?
Mm-hmm.
First half an hour, first like 1.5 hours, which all of you almost what? Almost died. Yes or no?
Yes.
Right? So are those rules again? Those rules we have to apply. You don't apply those rules, we are game over. So we are going to calculate our summation about first moment of area, and the first moment of area will be in the about the z-axis. Okay, will be about the z-axis. So from here, we know that this will be equal to the q of the flange plus by the q of the what? Of the web, right? We have to do q of the flange and q of the web. Okay, so from here, q of the flange, so it's ay bar. So we know that the general formula is q is equal to a y bar. Okay, so our q I like to do width multiplied by depth, y bar. Okay. So the width of the flange is 0.16. The depth, if we look at the depth, is equal to 0.02. And the first moment of area, the datum is from the centroid. So this is equal to 0.035, right? 0.035 minus by 0.01. So why that is, because the distance from here to here now, right? This distance, right? So this distance, we're talking about the flange now, yeah? So it's equal to 0.035 minus by 0.01. Okay. And then plus by the web. So the web, we have to consider 2. Why 2? Because you have what? Left and right. Okay. Then the area, the width is equal to 0.03. The width is equal to 0.02. And then the depth is equal to 0.015 minus y. Right? And then, so this is the area, yes or no? And then the depth, sorry, the y bar, right, is equal to 0.015 plus by y multiply by 0.5. I do apologize. I think I should put this here. Okay. So we know that this is left and right. This over here is the width. This over here is the depth. This over here is the y bar. Okay. So when you write this out, this will be equal to 80 times 10 to the power minus 6. Wait, let me calculate. So 0.03 minus by 0.01 times by 0.02 times by 0.16 equal to 80 times 10 to the power minus 6. Okay, plus by 4.5 times 10 to the power minus 6 minus by 0.02 y squared. Okay, so this will be equal to 84.5 times 10 to the power minus 6 minus by 0.02 y squared. Okay, and then we have to consider the shear in the xy direction will be equal to Vy over Izz, right, multiplied by Qz divided by T. Now, what is this T now? Okay, so the thickness over here, so you look at the thickness over here, so the thickness is what? 0.02, but you have to consider what? Left and what? Right. Okay, so the thickness, okay, the thickness is equal to 0.02 multiplied by 2. Again, the 2 over here is your left and right for your thickness. Okay, so from here, we write down the expression. So this will be equal to 90 times 10 to the power 3 divided by Izz is 5.8133 times 10 to the power minus 6. Okay, then multiply by 84.5 times 10 to the power minus 6 minus by 0.02 y squared divided by the thickness is equal to 0.02 divided by 2 for the left and right. So for this case, what you see over here, okay, so you will have 987.0435 times 10 to the power 9, and then multiply by 84.5